Okay, Maya, picture this. There is an AI model out there that is 50 times smaller than some of the biggest image editing models on the planet, and it still goes toe-to-toe with them. Not just close enough, it actually wins on several tests.
50 times smaller and it wins. That sounds like one of those headlines that falls apart the moment you read the fine print, so what is the catch here?
That is exactly the kind of skepticism I love, because there really is a fascinating story behind it. We are talking about image inpainting, which is the technology that fills in missing or removed parts of a photo, like erasing a stranger from your vacation picture and making the background look like they were never there.
Right, so think Photoshop's object removal tool or those phone camera features that erase photo bombers. I am guessing the big models that do this well are huge and slow.
Exactly. The current heavyweight champions are models like FLUX.1 Fill Dev and SD 3.5 Large Inpainting. We are talking about 8 to 12 billion parameters, which makes them gorgeous but also expensive and slow to run.
And this new model, called Moebius I am guessing, manages to compress all of that down to a fraction of the size. That is the part I want to understand, because usually when you shrink these models that aggressively, the quality just falls off a cliff.
You just described the entire problem the researchers were wrestling with. Moebius ends up at around 0.22 billion parameters, which is less than 2% of what Flux uses, and it still produces results that rival or beat it on multiple benchmarks.
Less than 2% of the parameters is a wild number. Before we get into how they pulled that off, why does anyone even care about making these models smaller in the first place?
Great question, because this is not just an academic flex. If a model needs a massive server with expensive GPUs just to erase a telephone pole from your photo, it cannot run on your phone. It cannot run cheaply at scale for a photo editing app, and it cannot be deployed on smaller devices at all.
So we are talking about the difference between something that only a huge company can afford to run in the cloud versus something that could eventually run locally on a laptop or even a phone. That is the real-world stakes here.
Exactly, and that tension is the entire motivation for this paper. The researchers basically asked themselves, can we build a much smaller specialist model that is laser-focused on this one task, instead of relying on a giant do-everything generalist?
Okay, that sounds reasonable on paper, but here is where my skepticism kicks in early. People have tried to shrink AI models, forever using tricks like lighter convolutions or simplified attention. Why would this attempt actually succeed where presumably others have struggled?
This is where the story gets interesting, because the researchers actually ran that exact experiment first, the naive shrink-it-down approach, and it broke spectacularly. When they took a strong existing inpainting model and just swapped in lightweight, off-the-shelf compression tricks, the quality of the generated images collapsed.
Collapsed, how badly are we talking about here? Give me a number so I can picture the damage.
Sure, so they measure image quality using a score called FID, where lower is better, since it is roughly capturing how different the generated image looks from real photos. Their solid baseline model scored around 32.75, but once they swapped in the naive lightweight components, that score jumped to over 43, which is a serious degradation in visual quality.
So just deleting parts of the brain made the model noticeably worse at its job. That tracks with what I would expect. You cannot just amputate complexity and hope for the best.
Right, and the researchers gave this problem a name. They call it a representation bottleneck. Basically, the lightweight building blocks were too simple to handle the rich reasoning that inpainting actually requires, like understanding where shadows should fall or how a brick wall pattern continues behind a removed object.
Let me make sure I understand that idea properly. Is this similar to trying to summarize an entire novel into a single tweet? You lose the plot, the character development, basically everything that made the story work in the first place.
That is a really good way to put it. A tiny model with naive compression is like that overly compressed tweet. It physically does not have enough room to hold the nuanced understanding needed. So the team realized that simply deleting capacity was the wrong move entirely.
So if deleting parts does not work, what did they actually do instead? There has to be some clever workaround here.
This is the heart of the paper. Instead of just cutting things out, they redesigned how the model pays attention to information in the first place, and they built two new components they call local lambda and interactive lambda.
Before you go further, I need to understand why attention is so expensive in the first place, because that seems to be the root of this whole problem.
Fair point, let me back up. In a typical AI model, attention works by comparing every single piece of the image to every other piece, checking how relevant they are to each other. Think of a chef in a massive kitchen who, before adding any ingredient, checks how it pairs with every single other ingredient in the pantry, one by one.
That sounds incredibly inefficient if the pantry keeps growing, because the number of comparisons would explode.
Exactly, that cost grows quadratically as the image gets bigger, which is part of why these big models are so slow and expensive. So instead, the researchers built a system where the model summarizes all of that contextual information into a small, fixed-size cheat sheet, rather than checking every single pair directly.
Okay, so instead of the chef checking every ingredient against every other ingredient, it sounds like the chef just keeps one tidy recipe card that already captures the important relationships. That would obviously be much faster to consult.
That is a perfect way to think about it. That is essentially what their local Lambda module does for understanding the local surroundings of the image, the textures and spatial patterns nearby a missing region, while still keeping that linear, fast complexity instead of the expensive quadratic kind.
And what about that second module, interactive lambda? What problem is that one solving?
Good catch, because this part addressed a specific flaw in earlier lightweight attention designs. Those designs were efficient at self-attention, basically looking within the image, but they had no good way to handle cross-attention, which is needed to bring in outside semantic guidance about what category of object or scene you are even looking at.
So it is like the chef who is great at organizing their own kitchen, but completely unable to read a recipe handed to them from someone else. That seems like a pretty big gap if external guidance matters for inpainting.
Exactly the gap they needed to close. Interactive Lambda lets the model efficiently fold in those external semantic hints. Things like, this is probably grass, or this is probably skin, using that same compact linear matrix trick instead of expensive attention maps.
All right, so these two modules fix the architecture problem on paper, but architecture alone did not seem to be enough, based on what you said earlier about the naive collapse. So, what was the second half of the solution?
This is where it gets really clever. Even with these smarter modules, the tiny model on its own, just trained the standard way, still landed at a noticeably worse FID score than the fully optimized version. So they brought in a teaching strategy borrowed from how humans actually learn complex skills.
You mean knowledge distillation, where a smaller student model learns from a larger teacher model. That is a known technique, so what makes their version different from the usual approach?
You are right that distillation itself is not new, but most versions just compare the final output of the student to the final output of the teacher, like comparing the finished dish at the very end. This team instead checks the work at multiple stages of the cooking process, not just the final plate.
So instead of a master chef only tasting your final dish and saying good or bad, they are also looking over your shoulder at the chopping stage and the simmering stage, correcting you along the way.
Precisely. They check alignment at a coarse, low-resolution stage to make sure the big picture structure is right, and separately at a fine, high-resolution stage to make sure the final details and textures line up with the teacher model, which in this case was an existing model called Pixel Hacker.
And presumably, they also had to balance how much weight to give each of those checkpoints during training, because focusing too much on one stage could throw off the rest.
You nailed it, and that balancing act was actually a real headache for them. The losses at different stages had wildly different scales, so they built an adaptive system that automatically adjusts how much each piece of feedback matters, based on the size of the gradient signal each one produces, instead of relying on fixed hand-tuned settings.
That sounds like an auto-adjusting thermostat for training, rather than someone manually guessing the right temperature every single day. Did this actually make a measurable difference, or is it more of an elegant idea on paper?
It made a very real difference. When they tested the model with only the most basic version of this training signal, the FID score was a rough 74. Once they layered in the full multi-stage distillation with all of its components, that score dropped all the way down to around 26, which is a massive jump in quality.
That is a big swing, and there is one more detail I want to poke at. You mentioned earlier that some of this perceptual quality checking usually requires decoding images back into full pixel form, which is expensive. How did they avoid that cost?
Smart catch, because that is actually one of the cleverer efficiency choices in the whole paper. They run the entire distillation process, including the perceptual quality checks, directly inside the compressed latent space, never decoding back to full pixel images during training.
So instead of working with the full-size, fully detailed photograph the whole time, they are working with a compressed blueprint version of it, which is naturally faster and lighter to process.
Exactly right. And that choice alone saved a significant amount of memory and computation during training, which mattered enormously for a project obsessed with efficiency from start to finish.
Okay, the engineering story makes sense to me now, but I want to move into skeptic corner for a minute, because impressive architecture diagrams do not always translate into impressive real-world results.
Please go ahead and pressure test this, because the numbers are genuinely strong, but they deserve scrutiny.
My first concern is straightforward. They are comparing their specialist model against generalist models like FLUX and SD 3.5. Of course, a model fine-tuned specifically for these benchmarks is going to do well against a generalist that was never specifically trained on them.
That is a completely fair point, and honestly the researchers acknowledge this distinction themselves. Moebius is explicitly a task-specific specialist, fine-tuned separately on each benchmark like Places 2 or Celeb HQ, while Flux and SD 3.5 are zero-shot generalists that were never tuned on these specific datasets at all.
So this is not really a fair fight between equals. It is more like comparing a dedicated specialist surgeon to a brilliant general practitioner and declaring the specialist superior at heart surgery specifically. That context really matters for how impressive the headline numbers actually are.
Completely agreed, and that nuance is important context for anyone reading the headline numbers. That said, the comparison still matters practically, because if you only need a model for one specific job, you do not need to pay the cost of a giant generalist anyway.
Fair, that is a legitimate real-world framing. My second concern is about the human evaluation. They ran a user study with 22 participants choosing their preferred result between models. 22 people is a pretty small sample to draw sweeping conclusions from.
Also a fair critique, 22 participants is on the smaller side for a study like this. The researchers did try to make it rigorous though, running it as a double-blind forced choice test with both expert and general participants across 50 cases each, in natural scenes, portrait scenes, and real-world object removal.
Double-blind and forced choice does add some credibility, since people could not just say everything looks fine. Still, I would want to see this repeated with a much larger and more diverse pool of evaluators before fully trusting the percentages.
Totally reasonable, and that is exactly the kind of follow-up work this paper should invite. Even with that caveat, the directional result lines up with the numerical FID and LPIPS scores reported separately, which adds some independent confirmation beyond just human opinion.
Okay, third concern, and this one is honestly built into the paper itself rather than something I am digging up. They openly admit Moebius struggles in certain situations, specifically tiny background regions with very limited surrounding context.
Right, and I actually really respect that they included this failure case analysis instead of hiding it. When the area needing to be filled in is extremely small and surrounded by very little usable context, the lightweight model can produce slightly less convincing detail compared to its larger teacher model.
That makes intuitive sense given everything we just discussed about the representation bottleneck. You compress the model successfully for most situations, but there is presumably still some ceiling on how much nuance a much smaller network can represent, especially in the hardest edge cases.
Exactly, and that is a really honest way to frame the overall trade-off here. This is not a free lunch where you get giant model quality with zero compromises. It is a carefully engineered trade-off that wins on almost everything that matters for practical deployment, while accepting some loss in the toughest corner cases.
All right, I think those are fair caveats, and they actually make the result more credible to me rather than less, because the researchers are not overselling it as flawless. So let us talk about why any of this actually matters outside of a research lab.
This is where the practical implications get exciting. Because Moebius is so much smaller and faster, roughly 15 times faster in total inference time compared to FLUX. This kind of approach opens the door to running high-quality object removal and photo restoration directly inside everyday apps, without needing a massive cloud server behind every single edit.
So think photo editing apps on your phone doing convincing background fixes locally, or smaller companies being able to offer professional-grade inpainting features without needing the budget of a major tech giant to run the backend infrastructure.
Exactly that kind of accessibility shift. There is also a real-world object removal demonstration in the paper, showing the model successfully removing things like an electrical pole or people standing near a riverbank. Scenarios with irregular, messy, real-world masks rather than the clean benchmark masks used in academic testing.
That real-world test matters a lot to me, because academic benchmarks can sometimes be a bit too tidy and forgiving compared to actual messy photos people take in everyday life.
Completely agree. And that is exactly why that section of the paper carries real weight beyond just chasing leaderboard numbers. Zooming out a bit further, this whole approach also offers a broader lesson for the AI field generally, which is that bigger is not automatically the only path to better.
Right, there has been this dominant assumption across the industry that scaling up parameter counts is basically the main lever for improving quality. This paper is making the case that smart, targeted architectural redesign combined with careful teaching can sometimes get you most of the way there for a fraction of the cost, at least for narrowly defined tasks.
Exactly, and that distinction between narrowly defined tasks and broad general capability is the key asterisk here. Nobody is claiming a 0.22 billion parameter model could replace a giant generalist model across every conceivable creative task. But for a well-defined job like inpainting, this is a strong proof of concept that efficient specialists can compete with giants.
Which makes me curious about where this kind of technique could go next. Could the same local lambda and interactive lambda idea, plus this multi-stage latent space distillation, be applied to other generative tasks beyond just inpainting?
That is a very reasonable direction to imagine, even though the paper itself stays focused specifically on inpainting. The core ideas here, summarizing context into compact linear matrices instead of expensive attention maps, and teaching a student model at multiple levels of detail inside latent space, do not seem inherently limited to this one task. So future research extending this toward other image generation or editing problems would be a natural next step.
So the real headline is not just one clever inpainting model. It is a blueprint for how to responsibly shrink powerful generative models without breaking them. As long as you are willing to redesign the internals thoughtfully instead of just deleting pieces.
Beautifully summarized. The big lesson here is that naive compression breaks complex AI models, but thoughtful architectural redesign paired with a smarter teaching process can let a tiny specialist genuinely rival giants 50 times its size, at least within its own specific lane.
And that is a wrap for today's episode. If you found this conversation valuable, consider subscribing and turning on notifications because we release new research breakdowns regularly, helping you stay on top of the latest discoveries without having to read every paper yourself. Thanks for listening, and we will see you in the next one. Goodbye.